Hello, everyone, and welcome to chapter 21. We're going to be talking still about carbonyl chemistry, just not reacting with the pi bond directly. We're going to be utilizing that pi bond and looking at some other, remembering some of our old ideas of ketones and aldehydes. We're going to be talking about the alpha carbon. And so we'll define what the alpha carbon is, and then we'll talk about enols again. And we'll talk about a new type of functional group called the enolate. So when we're talking about alpha carbons, this is where an enol or an enolate is going to start to react with the alpha carbon or be a part of the functional group. Greek letters are used to describe the proximity of carbons and the relative to the carbonyl. So the carbonyl is kind of like our home plate here. That was our electrophile in the previous chapters. Now the alpha carbon that we are going to be discussing in this chapter is the adjacent next door carbon. That's what we're talking about. And this chapter is going to explore the reactivity at this specific position. So alpha protons are the protons attached to the alpha carbon, right? So we can say if this is an alpha carbon, it's adjacent to the carbonyl, that hydrogen is an alpha proton, right? Now, we remember, hopefully, that enols can be produced in certain reactions of alkynes. Carbon-carbon triple bonds can use acid catalyzed hydration or hydroboration oxidation to create an enol. So we have seen enols before. It was way back in chapter 9. And they tautomerize to ketones. We are going to be utilizing that relationship between the enol and the keto form in all of these reactions. Now, if a catalytic amount of acid or base is used, we go from the ketone to the enol form, which again, ene for the alkene, all for the alcohol, so enol. Again, notice the alpha carbon is now the one that has the pi bond and the oxygen has the hydrogen. If we use a strong base though, we actually can get a deprotonation of the alpha carbon, which creates an enolate. Notice again, the pi bond is there between the alpha carbon and the carbon of the carbonyl, but instead of an alcohol, we have an oxygen with a negative charge. Most of the reactions in this chapter will proceed via an enol or an enolate intermediate. So in the presence of an acid or base, a ketone or an aldehyde can exist in equilibrium with its enol form, right? We remember that they were tautomers. Yes, generally the ketone, the carbon-oxygen double bond, is more favorable than the carbon-carbon double bond, which is why we always tautomerized to our final product last semester to the carbon-oxygen double bond. This is typically more stable over here on the ketone side. And that's due to the carbon-oxygen double bond being more stable than the carbon-carbon double bond. However, they are in equilibrium. Both are present in a sample of ketone or aldehyde, all right? Gotta love the memes. If you ever watched Scooby-Doo, not sure if that was way too past your time, but they always discover who's the villain at the end, and he says, I would have gotten away with it if it hadn't been for those darn kids. Ketones and enols are constitutional isomers, but essentially they are tautomers, right? There's a special relationship between these constitutional isomers that makes them more closely related than our typical constitutional isomer. All right, there are exceptions to the idea that the ketone is more favorable. The diketone, which we will be talking about later on, is actually more favorable in its enol form. And it's most likely due to the idea that it is stabilized by conjugation with the second ketone. So notice how this ketone stays the same and the other ketone converted to an enol. And it does exist in a relatively high abundance in this enol form, probably due to conjugation between the alkene and the carbonyl that's left over, and intramolecular hydrogen bonding. Remember, we've talked about 5 or 6 membered ring interactions. 1, 2, 3, 4, 5, 6. There's your 6-membered ring that is causing that hydrogen bonding to be favorable. Now, this carbon right here is the alpha carbon, right? There's the alpha carbon. And so it is sandwiched in between 2 carbonyls. So we still do have an alpha carbon there and some alpha hydrogens. The 1,3-diketone is specific to us in this chapter because it is relatively reactive at that alpha carbon. Phenol is another example where the enol is vastly favored over the keto in the equilibrium form, because phenol is in the enol form is stabilized with aromaticity. So let's just remind ourselves what the mechanism is for tautomerization, whether it is in acid conditions or base conditions. These are both catalyzed reactions. So we use our acid or base in the first step. We do some resonance, and then we'll reform our acid or base. Here's the first one for an acid catalyzed tautomerization from the keto form to the enol form. We just simplify ketone here for the keto, meaning the carbonyl form, right? And the enol, meaning the carbon-carbon double bond form. All right, so protonation, right? We're going to protonate that oxygen of the carbonyl, and then this creates resonance that is a resonance stabilized cation, carbocation at the carbonyl position. And then another proton transfer, we will deprotonate the alpha hydrogen, the alpha proton can then deprotonate and roll those electrons down to be a new pi bond. All right, so it's 2 proton transfers with resonance sandwiched in the middle. Same idea with the base conditions, proton transfer, resonance, proton transfer. Notice here, we're going to start with a deprotonation of the alpha carbon, pull off that alpha proton with our base, pop a lone pair on the alpha carbon. I'm still going to keep trying to label alpha here just so that we start recognizing it as a form of reactivity. There's resonance to stabilize that anion. And then we pick up a proton again. Proton transfer followed by resonance, proton transfer. Keto to the enol form, just under base conditions. Notice it's just reversed, whether we're protonating the oxygen or deprotonating the carbon. All right, it is safe to assume that some fraction of ketone and aldehyde in a solution will exist as the enol form at that alpha position. And that alpha position is nucleophilic, right? So when we're looking at this resonance here, we can imagine the resonance hybrid looking similar to this. Oxygen would get the delta plus and the carbon would get the delta minus. This is the resonance hybrid for an enol in resonance. So in the presence of a strong base, the enolate can actually form. So there is an actual pKa here associated with this alpha proton, and that's what we're going to be diving into in this chapter. The enolate is much more nucleophilic than its enol because it carries an overall negative charge, right? The resonance hybrid for this structure has 2 delta minuses, because now we have an overall minus charge because we deprotonated the ketone rather than just did an enol tautomerization. So Enolates can actually undergo a carbon attack or an oxygen attack. Most likely what we are going to see is the carbon attack. Why? Because it reforms that carbon-oxygen double bond, and the carbon-oxygen double bond is extremely stable. So either way, when we think about the oxygen holding the negative charge or the carbon, what we typically see is a carbon attack like this. So even in this first structure, oxygen would roll its lone pairs back down to create that very stable oxygen to carbon double bond. And then the pi bond would go and attack an electrophile. Specifically, it's the alpha carbon that is taking those pi electrons and picking up the electrophile. Same thing over on the right-hand side. The alpha carbon has the negative charge in this resonance form, and therefore it is the nucleophile. Most of the reactions in this chapter are going to be dealing right here with enolates attacking an electrophile. So alpha protons are the only acidic protons on an aldehyde or ketone that can be removed to form an enolate. If you want to think about stepping back further away from the carbonyl, it's not going to happen. Why? We lose resonance stability. The beta or the gamma, right? If you think A, B, C in Greek, alpha, beta, gamma. Beta and gamma protons are not acidic. There's no resonance stabilizing them, so deprotonation will not occur. Here are some pKa values of some specific ketones and aldehydes: acetone, acetophenone, and acetaldehyde. So you see that it ranges for ketones and aldehydes around 16 to 20, let's say. And so we have to consider this pKa value when we're looking at a proper base to form an enolate, right? Remember, so these pKa values have to be lower than the pKa of the conjugate acid. So let's look at all of our different range of pKa's here for alpha carbons. Notice how all of these are alpha carbons, and we will be seeing a variety of these throughout this chapter. Yes, even amides, esters, diesters, the beta ketone, beta diketone, beta ketoester, will all have alpha hydrogens, and those pKa's range from 9 to 30, ranging because of induction, right? So if we think about nitrogens and oxygens, they push electron density towards the carbon of the carbonyl via resonance and induction. And so those raise the pKa slightly. Aldehydes and ketones are right down in the middle, around 17 to 19. When we institute resonance between two carbonyls, an alpha carbon sandwiched between a diester or a beta ketoester or a beta diketone, all three of those on the right-hand side have drastically dropped their pKa's. So they're not super acidic, but they're definitely a lot lower than our typical sp3 carbons to hydrogens. And the reason for that is more resonance, more stability of the conjugate base, right? So these pKa values I expect you to be able to utilize and to understand, and we'll be picking our bases based off of these numbers. So looking at the aldehyde first, we'll take our simple acetaldehyde here. Alpha carbon with a pKa of 16.7. If we think about ethoxide or methoxide or ethanol, sodium hydroxide, we see that we could imagine the acid-base curved arrows, but look at these pKa ranges. They are so close. When an alkoxide is used, an oxygen with a minus charge, when an alkoxide is used, the enolate nucleophile, right, can react with the ketone, as we'll see in a later chapter. But notice here our arrows are resonance arrow or equilibrium arrows, equilibrium arrows. And those equilibrium arrows favor the ketone form rather than the enolate form, or the aldehyde form rather than the enolate. And so that's going to be something very, very important. This is a reversible reaction. To irreversibly and completely form the enolate, stronger bases must be used. One stronger base that we have seen before is sodium hydride, NaH. NaH is really, really good at deprotonating alpha carbons because H2 gas is formed. H2 gas not only bubbles out of solution, but remember its pKa is 35. So again, if we're thinking pKa around 16.7 here, we see that as we go from reactants to products, the product conjugate acid pKa is much higher than that of the reactant acid. So therefore, products are favored. Excellent. LDA, lithium diisopropyl amine, is also really, really good. Now, how LDA is formed is by treatment of diisopropyl amine. This proton right here gets deprotonated with butyl lithium. And this beautiful LDA structure is what can go into reactions as a very strong base. Why is it a great base? It's large, so it doesn't want to substitute. And it is a nitrogen with a negative charge. It is very, very reactive. When LDA is used to form an enolate, the amount of ketone present at equilibrium is almost zero. We will see that nitrogen can deprotonate the alpha carbon, pKa 36 for the conjugate acid, which is 20 times higher than the pKa of the original acid, which means, again, log base 10 scale, 10 to the 20 times more product. That's a lot of product compared to reactant, right? Log base 10 scale, that pKa, don't forget about that. So LDA features two bulky isopropyl groups, which allows to be a strong base, but not a good nucleophile. Too much steric hindrance. All right, so thinking about what we just covered with choosing a base or an enolate formation, there will be some times when we want to take aldehydes or ketones in an equilibrium reaction to form the enolate. Sometimes we're going to want to just have only irreversible enolate formation. All right, so we're going to see those two in just a few moments. If you have one of our dicarbonyl compounds, one of the carbonyls that had the pKa range extremely low, when we see those, LDA is actually not even necessary, right? If the pKa is less than 16, right, less than the conjugate acid of hydroxide or ethoxide, then it's nearly completely enolate formation, right? So when we're thinking about the pKas of a dicarbonyl ranged from about 13 to 9 for the pKa. All of those are less than the pKa of water or an alcohol, right? Those pKas are around 15 to 16. So no matter what, you don't need LDA. Don't waste the money using a really, really strong base when sodium hydroxide does just fine. The pKa of that dicarbonyl compound in its alpha proton position is already a lot lower than that of the conjugate. So good to just go ahead and use sodium hydroxide, sodium ethoxide. Sodium methoxide will also see this, this chapter as well.